Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. As we approach TWIMLCon AI platforms, I'd like to let you all in on our first major announcement from the conference. Now, you all love this podcast for great guests and interviews, and we're bringing that concept right to the TWIMLCon stage. I am super excited to announce that Andrew Ng will be joining me on stage at TWIMLCon for a live keynote interview. Many of you know Andrew from his work at Stanford, Coursera, or his many other efforts in the industry, including recently founding deeplearning.ai. Andrew and his work have been super impactful on my life and career, and I know that's the case for many of you as well. In our conversation, we'll be discussing the state of AI in the enterprise, the barriers to using deep learning in production and how to overcome them, his views on tooling and platforms for efficient AI delivery, and other topics from his recently published AI Transformation Playbook. Be on the lookout for more great speaker announcements rolling out over the course of the next few weeks. You don't want to miss this event. Get your tickets now at twimlcon.com/register. All right, everyone, I am on the line with Zach Lipton. Zach is an assistant professor in the Tepper School of Business and an affiliate faculty in the Machine Learning Department and Hines School of Public Policy at CMU. Zach, welcome to This Week in Machine Learning and AI.
Thanks for having me.
Let's get started by having you share a little bit about your background. How did you end up in this intersection of business, machine learning, public policy, lots of different areas?
That's a good question. I'm not sure completely, but I can't really, to be completely honest, I can't claim it was planned or anything. I think if anything, maybe it came from sort of just doing what I wanted to do at every given point and not following a very specific path that was laid out, and as a result, wound up maybe someplace different than the standard thing.
You recently transitioned into your professorship at CMU from your PhD. What was that in?
So I did my PhD in computer science. I kind of had a circuitous path. I had a circuitous path to PhD and out of PhD, but I did my undergraduate in math and economics at Columbia. That was a long time ago. And I was a musician sort of before, during, and after, and that was my main thing. I was playing the saxophone, and I wanted to, be a hustling jazz musician, which is a hard life, I think, even if you're the very best and luckiest, but certainly if you're not the luckiest. So I was doing that for a long time. After, I think I was happiest playing music when I was in undergrad, and there was this kind of amazing balance about being at Columbia and having the academic side of my life be a little bit more on the technical side, which felt more natural for me, at least within academic environment. Like I enjoyed, like jazz music is sort of a folk music, and there's something very organic about learning that music as an oral tradition and learning it by spending your nights out until 4 a.m. playing it with people who speak that music or who play that music kind of natively. And there was something that I never quite loved about taking classes in jazz music, like in a university or conservatory setting. It always felt a little bit artificial. I think maybe other art forms might be more amenable to that. And so I guess after spending a certain amount of time playing music, being outside, I had some personal setbacks. So I was hemorrhaging money and living in the Lower East Side. And the only way I was able to live in the Lower East Side is I was in a rent-controlled apartment. And usually that means that, unfortunately, New York was kind of neglected by the landlords. And so it was like a moldy apartment. There's people vomiting on your sidewalk and all that. And then I went out and visited a friend who's actually a musician who was doing a PhD in music composition. So he was a jazz musician, but he was an amazing pianist and has, the kind of rounded chops that he could also make it in a composition program. He came out and started a graduate program at UC Santa Cruz. So I came out and visited him. And I didn't want to go to grad school for music, but that experience of being out there and like after just kind of being in this sort of falling apart type state in New York City in this rundown apartment and feeling unhealthy and everything, then I was out in Santa Cruz, and Santa Cruz, like the sun is shining. It's the most beautiful place in the world.
Santa
The
Cruz is
90-year-olds, the 90-year-olds look 30 years old. Um, and then they, this group of composers would get together every week, and they had these listening sessions, and it was almost like a reading group. Like they would, like it was very different than maybe like my experience in music, which is being a social music was hard to have like a kind of critical intellectual discourse about it on the level, because you sort of were, it was very personal to people, and you were trying to get gigs working with people. And I felt like there was like this missing part of my life that, this like very academic / New York thing in me that just wants to like have very like candid arguments with people about things. And I was in Santa Cruz, and it was just beautiful, and everything was amazing. And these composers would get together once a week, and someone would curate, and they'd play a bunch of music, and then people would just scream at each other about it, and like really, not in an ad hominem way, but just really, express really, really strong kind of critical opinions about it. And there was something about this environment that made me think, like that, oh, that's it. Like it wasn't that I want to go to grad school for music, but I was like, oh, I'm going to move to California. I'm going to do a PhD. I'm going to get into that kind of environment where I feel like I have that kind of intellectual life.
Mm-hmm.
And so I went back home, and I got my landlord to agree to let me break my lease early. I asked my parents if I could steal our old 2004 Toyota Corolla. I signed up to take the GREs, and then I was like, I'm going to go do a PhD. And I hadn't even decided what the PhD was going to be in. Mm. So then the next step was well, what am I going to do? And it actually came together, this whole really just kind of ridiculous, unqualified plan to do PhD came together extremely fast, 2 to 3 weeks. It was just kind of all set up. It just kind of, I don't know why. I didn't even know what machine learning really was, but I knew I wanted to do PhD. And I had a good friend who was had been a bit of a mentor for me, who was a biophysics professor. And I taught myself to program a little bit, and I built him a website. And so we would hang out and play chess sometimes and drink coffee. And he used to invite me to the reading group. So I had a little bit of a sense of what academic life was like, even though I don't really know biology or physics. And he was just always, for some reason, he took an interest in me, and we were close. And so I talked to him. I was like, maybe I should do PhD in biology. And he's like, that's not fun, it's a top, he's like, that's a top heavy. Basically, it was like, that's, it's a great job, and it's an amazing field if you're on top. But he's like, it's going to take you 6 years to figure out how to be a useful lab tech before you can even start doing anything creative. And by that time, you're going to be, on your way to 40 years old. That's not the route. And we thought about it some more. It's like, what to do is I taught, I'd taken only 1 or 2 undergraduate computer science classes, but somehow that felt like the right thing. Mm-hmm. There's something just really, I think a lot of people have it. The first time you learn computer science, you learn about algorithms, and you suddenly start learning how to think about how to start formalizing things you see in the real world. How would you model that computationally? And then you start thinking about things like the structure in real world problems that makes them amenable to efficient algorithms. Something about that kind of clicked with me when I was young. So even if I hadn't sort of followed up on it, just having these 2 or 3 undergraduate computer science classes made this impression on me. And I knew how to program just enough to cause trouble. And so I thought about it. I was like, well, that's the thing I can maybe sort of run with, but that was, it was a very thin basis to hang my hat on. But fortunately, when I applied to PhD, there were some people who were willing to take a chance on me. And one of them was UC San Diego, which is a absolutely fantastic school that everyone in the world should apply to if you're interested in computer science or surfing or beautiful weather, just building a new life.
Sounds like you pattern match Santa Cruz pretty well, except for maybe 8 degrees warmer on average or something.
Yeah, it's a bit warmer. It's, they both, I think, have the year-round moderate weather thing kind of happen. They both have the surfing. I think Santa Cruz is a bit hippier. San Diego has multiple sides. Like you've got the La Jolla kind of stuffy Mitch Romney kind of side, and then you've got you got a lot of Navy presence there, so that's a big player in San Diego. But yeah, you've got that beautiful year-round weather, and that attracts something cool. Mm-hmm. Great food also.
And so did you just jump right in, take some courses, find your way to machine learning, or what was that initial connection to the world of ML?
Well, ML was just the thing from the start. Like that was I didn't know any ML. Like literally, if you told me to like write out, explain to you on the whiteboard, like a classic algorithm, like logistic regression or something, I would not have known. I would not have been able to do it, or explain gradient descent. Like I hadn't ever implemented a machine learning algorithm, but what I knew was that I spent 1 year in San Francisco, 2012. So like when I made this plan, there's one problem with the whole grad school pipeline, which is that it's a great pipeline, or maybe people have some fault with it or something, but overall, like it works well if you're already in the system. So like if you're an undergrad and then you want to go to master's, you're like, well, I'm a junior now and I got to start thinking about that. And you do it and you're not like off the path while you're making that plan, right? Mm-hmm. But the trick is if you're doing something completely different, if you're like, I'm playing a saxophone at 3 a.m. For $40 in some weird dive that's going to close down in a couple months, and I want to go do a PhD, then it's like you're out of the system. Like, what are you gonna? So this was like spring 2000, like end of spring 2012 is what you need. That's like your last moment to make a move, like a serious, like hard turn, even if you play everything right, to like get into PhD for fall 2013. Mm-hmm. Right. So you have to kind of not just like have this thing come together, but you then have to somehow stick with it despite not being like in that rhythm for some period of time. So my move was basically, I knew that if I stayed in New York, I would just keep doing what I was doing. So my move was to like break my lease, sign up for the GREs, get that part out of the way because that was the part that I knew about, and then move to California. And I was like, well, I'll basically go to San Francisco and maybe find a way to be a lemming for a startup or something until while I'm putting that together. But at least I wouldn't be like in New York still hanging out till 5 a.m, like trying to hustle for gigs, because I'd be out of, and it just also felt natural, like change your life, change your location, like to wake up every morning in a new place. So I moved to San Francisco. Actually, I did everything weird. It was a really wild time. Like I lived in one of these like totally could not possibly have been legal. They call them like hacker hostels or something.
Oh yeah.
Like I have this like problem, which is maybe part of why I have wound up in all kinds of weird situations. But if you can cast like a situation as a choice to have an adventure or not have an adventure, and that's like a valid lens on the situation, then I'll choose the adventure. and so I read I was thinking like San Francisco, like, whatever, Silicon Valley, whatever, it was still a little more romantic at the time. I think in 2012, it wasn't quite as like evil empire as it is now, but it was already pretty expensive. And there was these articles in the New York Times about these weird hacker hostels where like people would rent them through Airbnb for like a month at a time, and they were like packed in. And so I went out and I lived like literally in a bunk bed with 6 people for a month until
trying to make it big in Silicon Valley.
And just trying to I don't know what it was, just find out what it was. Like I didn't know anyone out there, so like at least I'll meet some. And it was all like Germans. Met like a bunch of Germans who were hanging out for a minute. Yeah, they love their hostels. Yeah, so I moved to California, biked the California coast, and then set up in San Francisco and lived in this weird Airbnb for a minute. And then I moved out to Oakland, and that was great. I actually ended up playing a lot of jazz again when I was in Oakland and getting to know that community. I worked with a startup, and then spent a significant portion of my time then applying a PhD. And I got lucky that someone took a chance on me.
Nice. And so you applied to ML programs?
Not to be all CMU chauvinist or something, but I think CMU is unusual in having an ML program, and was in the past was exceedingly unusual in having like an ML department. Like So I applied to computer science, and you check off maybe some interest areas or something, but it's not like a separate program you apply to computer science. I think now things have gotten weird enough that you look at a typical school has a typical university has a school of engineering, within it a department of computer science, and within that some subgroup of people, some working group that works on machine learning, not as like a formal distinction. Although maybe there's some kind of committees or they band together for making hiring decisions or something, but that's how it works. CMU is very unusual because CMU has a school of computer science, and within it, department of machine learning, a department of robotics, a department of natural language. It's called Language Technologies Institute, department of human computer action and stuff like that. So at the time of applying, most of the places you apply, you just apply to CS, and maybe list your interest. I think now things are getting weird because I think more places are copying the CMU model as places try to keep up with the demand, especially for like courses in AI and machine learning. Mm-hmm. I think the other thing that's happening is just a lot of schools I've heard from colleagues who are professors elsewhere that, at a lot of CS departments, you'll get maybe CS will be like 6 faculty out of 50 or 40 or something. But maybe 50, 60% of the applications for grad school for PhD are people saying they want to do machine learning, right? So that creates a whole other dynamic where maybe they end up treating it, even if it's not formally a separate application, they have to throttle it a little bit because they're thinking, well, who are these people going to work with, right?
Right.
And the alternative is you accept them all, and then the half of them get the advisor they want, and the other half end up doing compilers or something.
Let's maybe talk a little bit about your broad research interests nowadays. What are you focusing on?
Well, I think the lens, there's a few kind of lenses that I have in research, right? There's, a lot of people are more applied. A lot of people are more like theoretical or core algorithms. And I kind of straddle that line a little bit. And on the applied side, my biggest interest has been since before I started PhD, and has continued to be throughout, and as a young faculty member, has been working in machine learning for healthcare. So that's kind of, if I had to step back and think about not, papers in terms of like their aesthetic beauty or something, but in terms of like, if I could, build something big, like what would the grand vision be? It would be, I would like to have a positive impact in healthcare. And I think there are opportunities to do it. But at the same time, working on problems in healthcare, I think it's also a great application, not just because it's, much better for your soul than working on advertisements, but also because I think it just sort of puts you in touch with what's wrong, right? Because you just can't afford, like, it's too important and the stakes are too high that if you're going to go out there and say, this is how we should do decision making or something, or, we could, all these people, there's these sensational headlines, your next doctor might be an AI, and it's such absolute crap, right? But the reason why is because it really, if you really think deeply about these things, it puts you in touch with like the discrepancy between the tools that we have mastered and that we're building and the actual real world problems we're claiming to make some impact on, right? So the one hammer we have that everybody, is throwing all over the place wherever you can stick it in is called supervised learning. I'm sure you've talked about, machine learning. I guess,
sure.
You've run 9,000 podcasts already. And everyone who was talking about an actual working system probably was talking about supervised learning, right? There are limited exceptions where maybe someone just saying with bandit algorithms on advertisements. But for the most part, supervised learning is basically based on this idea that you're going to get data that comes in, right? And it's going to consist of inputs and corresponding outputs. And you're going to try to predict the outputs based on the inputs. And fortunately, what makes it supervised is that you, for the purposes of training, are going to have this large data set for which the outputs are known. So it's like someone's standing over your shoulder and telling you what the right answer is. And now the big assumption is that the data that you're then going to see in the real world, your training data was representative of it, right? So like basically the historical data and the future data are assumed to be what we call IID, which means they're like independently sampled from the same exact distribution.
Yeah.
And that's just a wild assumption, right? When you then think like, okay, wait a minute, so what can we do? It's like we can infer a likely output given an input, assuming that the future is in every like statistical way sort of, that the historical data is perfectly representative of the future in every, important statistical way. And that's just something that completely breaks down when you look at a lot of real world problems, right? So one thing that happens is that the historical data is not representative. So this is a question that, I think formally we talk about it in terms of what we call distribution shift. And distribution shift could be kind of benign, or not benign, but could just be kind of organic in the sense that it could be that, hey, Wednesday is different from Tuesday because it's different from Tuesday, right? So if you're classifying news articles or saying, well, people are, different stories are trending. More, if you're classifying by topic or something, there's more sports stories, today because Wimbledon is happening or something, or the Women's World Cup, and maybe there will be less 1 week from now. Who knows? So that's one way that things change. But then there's more insidious ways that things change, which is the other key thing is that we often, the machine learning problem, the formal statement's all about making predictions, but we're often not really concerned with making predictions. We're concerned with taking actions, right? It's all about driving decisions. If you're a company, you're talking about automation, and machine learning is coming up as this multi-billion-dollar concern, largely because of the hope that, what makes technology that valuable? It's something that you can do at scale. It's not because it's just people are doing offline data analysis or, trying to understand their customers qualitatively. It's because they're trying to drive decisions. Yeah. And once you start making decisions, now suddenly you're impacting the world, and very often that very same environment that generates your future data. And we just don't have great tools for understanding these kind of feedback loops, right? Once you take the data, extract information from it, and then use it to change the way that you make decisions in a way that, influences the world, everything kind of falls apart. And so I've done a lot of work recently trying to look at, well, under what assumptions can you make models, one, that are sort of guaranteed to be robust against certain kinds of distribution shift, to short of that, at least under what conditions, what tools can you use to try to detect as efficiently as possible, as quickly as possible, when somehow your environment has changed. And beyond that, to try to sort of gain some qualitative insight into, is that shift pathological or not? Is it something that you expect to break your model or destroy the validity of your predictions? You think about a medical setting, right? Like you're trying to you want to have the doctor AI. Your next doctor is going to be an AI. It's like presumably they have to be able to make treatment decisions, not just predict what would have happened if a different doctor, if the doctor who would have treated you anyway had done their thing.
So that's a bit of a nuance. How does that correspond to the distribution shift and the feedback loops that you were talking about? Because I think the fundamental premise of, as to your point, most everything we're doing here, which is supervised learning, is, we're going to collect this data that represents the sage wisdom of all the best doctors and train our models on it. And so then if, our models making the decisions, that are close to what our, the doctor that would have otherwise done them and does a good job at making those decisions, then everything is good and rosy.
Right. The problem is that, well, there's a number of big problems, but one is, one is that the world is changing naturally, right? And the actual doctor has some understanding of the biology of disease and is somewhat adaptable in this way, right? Like when we look at the ways that machine learning models break because you moved a few pixels in an image, that kind of stuff doesn't fool a human. So the humans are pretty robust, and I think actually this is something that my friend Jacob Steinhardt and I talked about in a paper about some kind of misleading trends or some problematic trends in scholarship, is that there's this tendency in papers to sort of make a kind of hyperbolic claim that isn't substantiated by the research. And one of the classic ways this happens is people talk about human level performance, right? So the human level of performance, it's not quite the right compare. If you're going to talk about sort of human capacity, the human capacity isn't just for doing doing well in this very, very constrained sort of like artificial environment that only exists when you truly have a randomized trained test split. The human dermatologist is going to continue to be a good dermatologist, even if the light contrast slightly changes on the images that they're looking at, right? Or even if the skin tone of the patients is different than it was in the training set. Problems where the machine learning potentially is going to fall apart in a catastrophic way. The other thing is, right, so there's an issue even with matching performance, because like matching performance, when we talk about performance, we're talking about accuracy. Often it's like, well, accuracy is itself a statistic, right? Accuracy is only true. It's only valid assuming a certain distribution of data. And if that's something that could change, like if the patient, something different happens, the patients start coming in with a different distribution of illnesses. Some disease starts becoming, that there's an epidemic. It's not quite, not every patient, you have to make adjustments to, what illnesses are patients likely to have given their symptoms, things like that. Yeah. The other side is that ultimately what you'd like to do is you'd like to not, the dream of machine learning is in healthcare isn't that we're going to somehow replace a bunch of doctors and in the process keep healthcare like slightly worse but almost as good. Right, like that's sort of what you're talking about when you're like, if you can predict when you talk about this imitation type learning thing. So a bigger dream would be that you would actually be able to assist the decision-making process. And so you'd be able to like ultimately the thing that gets most people excited isn't just say, hey, we're going to automate doctors, which, already maybe misses the point about just how much of the work is involved is not, taking the data that's already there and like trying to predict the doctor's decision, but it was actually meeting with the patient and determining which test to run in the first place, which resulted in the data, which actually was already all the work that the machine learning is not doing for you. So, that's another way that it's misleading. If we insert the machine learning at the end, we think we're doing what the doctor does, but it's like, well, what about those test results? Where'd they come from? Well, because someone who ordered those tests. So so then we also have to predict which test to order. And then given the test, we have to predict which disease. Given the disease, we have to predict, also which treatment they're going to recommend. And so, if you actually do a kind of fair analysis that puts together all the compounded errors that pop up and then account for a world that's constantly changing, things get messy. But then even on top of that, it's like our goal isn't to just freeze medicine at this point in time, get rid of all the doctors, and then just like put into place a machine learning algorithm that is based on what medicine looks like in 2018. What we'd like to do is to be able to understand disease processes better and be able to analyze data using, say, for example, models that don't just make predictions, but estimate treatment effects. So that's something we call causal inference. And ultimately, right, you'd like to be able to say, hey, if I intervene and do something different than what the doctor normally would do, what do I expect the outcome would be? Or which patients should I assign which drugs? Can we make a dent in personalized medicine? To do that, we're not just trying to make predictions about what people would have otherwise done. We're trying to figure out what are better things that we could do. And that requires causal inference. And causal inference actually now gives you a whole other lens on the ways that humans and computers potentially need to combine what they're good at. Because causal inference is not something that you in general can just do given offline data and no prior information. Causal inference actually requires certain inductive assumptions, certain assumptions about the causal graph or the mechanism that relates to data, or which things listen to which things. For example, like smoking causes cancer potentially, but cancer probably doesn't cause smoking. That'd be like a classic textbook example. But building in certain kind of advanced knowledge together with offline data, then we're able to potentially identify a causal effect even without running experiments in the wild. But we have to, I think ultimately, working on a task like medicine really exposes and thinking about what it would take to actually do something that you could actually run in the wild exposes you, makes you think about those things in a way that I think, maybe you should think about it if you're doing recommender systems. But the truth is that even if you don't think about it, there's going to be a large company that's willing to throw it out in the world and see if they make more money or lose money. And if they make money, is kind of going to roll with it, even if it's kind of doing the wrong thing, right? So we do that a lot with recommender systems, where it's like, what is the real task we're trying to solve? I don't know, curate interesting content. But what do we actually do? It's like we predict clicks. because that's the data we capture. So and that's another way that the contract breaks, right? I've talked about the way contract breaks because the distribution changes, because we actually interfere in the world, and that kind of messes with all the future data we see is now from a different world, the world in which, customers are interacting with this system that changes everything. But another way that the contract breaks is we're just predicting the wrong thing in the first place, because the thing we really care about is something where we don't capture as structured data, right? If you think about that, like with a lot of these issues potentially that make people worried and concerned about problems regarding, say, for example, racial or gender bias in automated systems, another area that I spent a lot of time thinking about and working on. One of the clear failure mechanisms is the data that you capture, that you model, is the thing that's convenient, not the true data. It's not the only way that things can fail, but that's one of them. And so you can imagine that you'd predict who to hire based on who the people hired in the past, but that's what you measure is who got hired in the past, or how are they rated by the interviewers in the past. What you don't capture necessarily is the thing you actually care about, which is how strong a candidate are they, which is a more abstract concept. So we end up relying on this thing that we have data for, which is not the same thing. And what is that consequence of sort of optimizing the wrong thing? And in the case of like YouTube recently, they had this scandal where the consequence was sort of curating pedophilia, or curating naked baby videos for people with this, So yeah, that's I think that's a especially dark or scary consequence. But this is something we have to think about is when the contract breaks, and I think by that sort of forces us to sort of go beyond just the narrow confines of doing and evaluating supervised learning models, where mostly the technical content consists of people just sort of squeezing out incremental predictive performance improvements, assuming the task is the right task, and sort of forces us to step back and think about either a more challenging or fundamental task like estimating causal effects, or thinking about the consequences of some of these systems, like using tools of, say, economic modeling. And that's one thing that's cool about sitting in the business school and having social scientists and economists as colleagues.
Well, talk to me about some of the economic modeling tools and applications of those tools in the space. What are some examples of how that plays out in healthcare and other areas?
I think the area where I personally am encountering economics the most, like I got hired by, kind of strangely early in PhD. I got approached by the Tepper School, who was looking to make, kind of move in a data science direct. I think I was a little bit of an experiment. And for a little while, I was a bit separated, I think. I wasn't like reading many economics papers or something. I was wrapping up, my kind of core like ICML NeurIPS type work. And actually two things that recently have put me in touch with them is one, starting to think a lot more about causality. You take a step back and say, well, who's doing empirical causal effect modeling in the world broadly? And it's largely social scientists and, like applied economists and econometricians, right? Like this is their bread and butter. There was some shock to this. Is it true that increasing the minimum wage decreases employment, or is that not true, right? And then you have these various ways of trying to draw these inferences from shocks to the system and the natural world, or various they have a handful of tools that they're kind of tried and true, like instrumental variable analysis, regression discontinuity, difference in difference. Some of these tools rely on some very strong assumptions, and I think can sometimes if those assumptions are violated, could lead to some wrong conclusions. But that's one way that I've kind of started crossing over. And I think, a lot of those tools are important because if you look at the work modeling, when you look at the effect of this technology in the real world, and you want to start saying, well, what is the impact of, especially when you have these fuzzy systems, right? Like risk scoring systems that are then driving policing decisions that are then influencing these outcomes. And it's very hard, from the machine learning standpoint, there's this big pile of papers that are just considering the classification aspect, right? I've got these people, they belong to this group, these people, they belong to that group. These are their inputs. These are the ground truth outputs. These are the predictions. Let me do some kind of arithmetic on them. But what you're not seeing is that like, oh, this system is generating a prediction. This prediction is some kind of score. The score is an input to a human who's making a decision. And if you actually care about the downstream problem, which is how is the introduction of this kind of system that is mining this information to make predictions, driving decisions, and influencing outcomes, then you start crossing over into a land where actually the people who have the experience doing this are the social scientists of actually looking at real world data and trying to figure out what are these various effects. And I think the other side actually is...
If I could jump in there, that's a really interesting point, because I think we often hear from the kind of the vendor community that's providing tools that are enabling these examples, these use cases that you're describing, that, hey, we're providing these tools to feed into a human decision process, as if that somehow means that there's not going to be anything wrong with the system, like the overall system, and also that we don't need to further like study and understand that overall system with the impact of these new tools in it. And I think you're pointing to that, well, actually studying, the impact of things like this is, something that we've been doing for a while, but just in other domains. And these are techniques that we can apply to these systems.
Yeah, absolutely. And I mean, there's a lot to say about that, right? On one hand, it's like, I feel like it's the easiest thing to say, which maybe is not as like intellectually profound, but like I think as like a public service announcement needs to be out there, is like, first of all, like, no, like it's almost a bit Orwellian. It's like, first of all, no, it's not okay just because there's an algorithm involved. But at the same time, it's also not just okay. It's not okay just because there's a human involved, right?
Right.
And there's a lot of issues to sort through, but both in terms of how we analyze these systems, also in terms of I think one of the fundamental difficulties in the area is also figuring out what is our goal, right? What is the right thing to do here? It's not always obvious. I think there are some cases that to us are like very obvious that something is wrong, but it's not always obvious what is the right basis for making certain kinds of decisions, especially when there's certain kinds of like intrinsic trade-offs. So there's questions about what's the right thing to do. The other problem is it's also, okay, so the big meta point there, I think, also is that, hey, these aren't new problems that emerge just because we stuck an algorithm in there. Mm-hmm. But they sort of get seen through a new light and get a new kind of attention. I think a lot of us in the machine learning community get stuck in this loop of sort of trying to you see a lot of people sort of talking about like AI ethics, which is great. It's great that people are trying to think about what is right and think about these sort of like social impacts of applying these automated systems. But at the same time, a lot of people are doing it because there's a little bit of a bandwagoning effect going on, right? Where a lot of people are jumping into it kind of completely oblivious of the fact that people have been mulling over like what are people, what are people's rights, and what is like an ethical way to engage in a lot of these systems even before machine learning was introduced. Mm-hmm. And I had the benefit of in early June, Cynthia Dwork, who's an absolutely inspirational researcher. She's the inventor of differential privacy and one of the pioneers in the more algorithmic fairness world. And Patricia Williams, who's a professor at Columbia Law. And they put together this fantastic workshop at the Simons Institute for Theoretical Computer Science. Mm-hmm. And so they've been branching out into some more like interdisciplinary type workshops. And this one was about sort of the race and data and injustice, and brought together people from. I liked it because you normally have this spectrum that brings together people who are working in computer science ML, and then like computer science ML adjacent. Like, I feel like there's a sweet spot that like the spectrum for interdisciplinarity runs from like information school type technical social scientist to theoretical computer scientist, and that's the spectrum, which is great. That's still very broad, and it's a wonderful set of people that I consider to be like in large part a lot of my, my home, like the people who you will meet if you go to like FATSTAR, right, the Fairness, Accountability, Transparency Conference. Mm-hmm. But the cool thing about this workshop is it brought together people like Ruha Benjamin, who is in Princeton and writes, teaches in like African American studies and has studied very clearly issues about race and technology in ways that transcend not just machine learning or this moment in time, but more broadly kind of history of ways that technology has been used as a tool that maybe exacerbates inequality. You had a lot of people from public health and epidemiology who were there. You had a lot of people who had been involved on the ethical aspects from like the medical ethics community in when genetics was like the big hot technology, and there were all kinds of ways that genetics was being used in ways that had kind of maybe like ways that were expressed kind of dubiously in terms of the ethical consequences, like various things, various sort of studies in population genetics that were sort of like neo-eugenicist type work, and there's been a long history here that is outside machine learning, I think, is where we came from this, and being in touch with that, and sometimes it's actually a surprisingly, when you come at it from the perspective of like us, a lot of people who are first thinking about these things and haven't like learned to, are only first thinking about it and in a relatively immature way, and go to an area, people who've been looking at, say, criminal justice and thinking about it and in a very mature way over a very long period of time, and have a really deep understanding of the kind of systemic problems in a way that goes beyond just kind of some trite formalism that maybe fails to capture the kind of like institutional level issues. Then I think that there's a lot to learn there. And I think this is also one of the big things that came out of it for me from that workshop that was, I think, a really kind of profound insight, was that we have a tendency in the technical community to try to reduce things to some kind of abstract problem. But there's a big danger that we can actually, I think a lot of us sort of purporting to work on problems of algorithmic fairness, but through a technical lens, by not understanding the broader context and not understanding the kind of systemic problems. Like, it's not just a matter of making the false positive rates equal between two groups or something like this, but actually understanding, stepping back of like, what does the data even mean, right? Or where was this data collected, or what, truly asking the kind of foundational questions about the broader system in which the kind of this formalism is embedded. We run the risk of actually doing what some people are calling fairwashing, which is that we could like take these fundamentally flawed systems where maybe the precise way that machine learning is being used there's something fundamentally wrong with it, and we could go in and say, oh, I'm into machine learning, I'm into social good, let me do some work at that area, and come up with a little tweak on the, there's a danger of coming up with just a small tweak on some existing algorithm, right? That sort of preserves precisely qualitatively what we're already doing, but gives somehow the impression that you've made it like fair, right?
I mean, that's kind of reflective of a broader argument, I guess, that's happening in the ML research community at large. The extent to which, these kind of revolutionary advances versus, incremental, with regard to publishing papers, like, a lot of the papers that we're seeing are kind of incremental application of some new training technique or something like that. And there is some commentary that, we're seeing kind of this huge exponential growth in the number of papers that are published, but some are arguing that the field isn't advancing, accordingly. And so this is this kind of fairwashing argument. On the one hand, the fairwashing element of it is different, but it's also somewhat reflective of kind of the broader dynamic that's happening in the research community. Would you agree with that?
Yeah. I mean, I think the broader thing that is kind of endemic is I think there's a lot of trends in the community, largely due to the success of the field and the fact that it's grown in such a really, I don't know if it's unprecedented in the scope of all fields, but it's unprecedented maybe in the scope of AI, machine intelligence, that has sort of resulted in this weird situation where the review system is buckling a little bit. The review system, the pool of reviewers has had to grow in a way that maybe changes the standards of who's a qualified reviewer. A lot of people are in a very volume driven. I think one of the things that happens is as the community grows so fast, not that many people are getting mentorship from, true masters in the field, but are really taking their cues from a machine learning subreddit or something, and are looking for a splashy or just trying to get papers in or get citations. So there's a lot of ways that the community maybe is struggling a little bit now in terms of quality control, and I think that maybe is a natural thing that'll self-correct as I think even this ICML was actually a step in the right direction. Then the other side is like this specific trend that you're talking about here, which is maybe this particular thing that we talk about maybe being a little bit abusive with language, misusing language, making one of the things about technical papers, even when technical review works, it has certain blind spots, right? Like if you submit a NeurIPS paper, you submit an ICML paper, you have an expectation. There are certain things the reviewers are going to, if the system works, be very critical about, and they are going to spot. And among them, you expect that they're going to spot if your notation makes no sense. They're going to spot if your theorem is wrong, hopefully. They're going to spot if your experiments don't sort of support the kind of performance claim that you are making in a like absolute sense, right? But what they tend to miss, and I think it's just a blind spot in the review, is the reviews are not generally critical about the sort of they're not able to assess the critical arguments that are made. And this is an area where, the typical ML paper is a bit sloppy. So the typical ML paper will, there's a caricature that you can make, which is that your introduction is just kind of, something is a problem and other people have worked on it, or it's, used to say some kind of generic mumbo jumbo. There's more and more data and bigger computers and something. And then you say something is a problem, and right now people have to do the work, and we can automate it with machine learning or something. But it's basically in too many papers, the introduction is not like an opportunity for like some profound philosophical argument that justifies why you're solving the problem you are in the first place. It's sort of a throwaway piece that just is some kind of stage setting, so you can move on to the meat of the paper, which is here are the equations and here are the quantitative results. And that leaves, And
is that the right bar for a paper, a profound philosophical argument? Is that the case in other fields?
Not for every paper, but in other fields it is the contribution, right? In other fields, like the argument is the substance of the paper. I think a philosophy paper, depending on which area of, say economics or something, that could be the essence of the paper, can be the critical argument that you are making, which is very different where we sort of get to that I have a very well-formed machine learning problem, and either I have an algorithm for it or I have a smashing empirical result for it. That is the and the sweet spot, I think, for like a NeurIPS or ICML paper, like the sweet spot from a perspective of like most likely to get in is something like that. I've got a very well-formed problem. Everyone's already decided it's important. I don't have to argue for its validity. And then you have the real sweet spot would be you had just enough of a algorithmic contribution that there's a non-trivial theorem in there. And then you also had some amount of experiments, because there's one of these things like whoever doesn't like your paper the most, it probably is going to get it, like there's some argument, I don't know, I don't know if this is truly true, but there's maybe a nugget of truth in it that like a paper doesn't get accepted, it gets not rejected or something like that. And so this way it's, the person who would say, there's no real experiments, I don't know it really works, that person is satisfied, and the person who their lazy way of accepting the paper is it's trivial, they get the math that they're looking for, then everyone is happy. But I think the language is a bit of a blind spot. Like, for example, it's extremely difficult to publish a position paper, no matter how well argued it. I think if you submitted an 8-page essay that like really meticulously picks apart, say, the foundations of some kind of problem or some kind of application of machine learning in a way that it's extremely knowledgeable or well researched or whatever, I think you'd have virtually no chance of getting it accepted at ICML or NeurIPS. I think the NLP community is a bit better. Like some of their conferences will explicitly, if not, say that's the number one priority, and I don't think they should. It's a technical conference. Will at least include position papers as like within the mandate of the conference. Where you do have a little bit more license for something like that is a lot of workshops are friendlier to that kind of material. But, I think the danger is what you end up getting is what you get is a technical paper that maybe it makes technical sense. I mean, even there, I think we have some weird issues, but that's a whole other, topic. But, even say the technical content of the paper makes sense, what you have is a problem which is ostensibly valuable in part because of the virtue signaling that it is addressing some important real world problem, right? So you start from that point, but then the claim maybe, the paper says like, we make our algorithm fair by doing whatever, this is the fair DQN, the fair GAN, the fair whatever it is. So the claim, like from the very title of the paper, is the claim is somehow we have satisfied whatever it is, this thing called fairness.
Fairness check.
We've made the ethical reinforcement learning agent or something like this. So like the claim is sort of at the outset it's not like a firm technical mathematical claim. It's sort of like we solved ethics or something like this. And then the introduction very often, for and I'm not saying every paper is like this, but I think there's a pattern where the motivation might either be, on the worst side, it could be, there's plenty of work that's just like babbling. But on the other side, you could have work that is even intelligent, but it's just that the applicability to that real world problem that you're claiming that you solved is just missing, or it's not there, or there are serious caveats that need to be stated. And then you have these weird things that you have to argue that your quantitative result is correct. You have to argue, you have to be meticulous about laying out like how you did your splits between train, validation, test data. How many runs did you do? Make sure that your work is reproducible by communicating certain technical details. You have to put the proofs for the theorems. You can't just make a outlandish claim that some mathematical fact is true. You have to prove it, right? But then there's things that you don't have to prove. And I think these are subtle ways that things go wrong. Like, for example, you don't have to argue for what you call something. And some reviewers might get pricked, or they might be particular about language, but I think a lot of people are willing to let that slide. And this becomes, I think, especially a problem in this new dynamic where the research isn't just among the research community, right? It's not just technical research that's being read by PhD students. There's this weird loop between research, industry, governance, and a huge part of that is the popular press. And so you wind up in a system where it's like people are maybe motivated. I think people I don't think are malicious. I think you wind up with someone maybe motivated by a genuine desire to do something that they feel has more social, sort of some kind of positive social impact or something like that. But then they start working on it and they think, well, how am I going, what would be a good title for this paper? It's going to get people to read it or something, and they're not necessarily thinking like, hey, I'm making a claim that this is this thing that solves there's this real world problem. And I'm making a claim that this algorithm that I'm putting, which solves some very sort of like toy, very reductive version of that problem that has some applicability to that real world situation, which it might not. Right. And then, people you put out this thing like, I'm gonna, my thing will tell you if your algorithm is fair or whatever, without even being clear about have we even addressed like the right ingredients? Are we even speaking in the right language to be able to capture something like that? And do we even access the right data or any of that? And then it gets picked up in a story and say, for example, like IBM has been a bit of a like cavalier actor in this way, right? Both with medical and with fairness related things, right? So IBM did this thing where, with Watson forever, where they kind of made people think they were solving fundamental medical problems when they really didn't have the goods to back it up. And then now it's like, oh, we're getting ahead of the fairness thing, which is, it's great that on one hand, they're running this ad campaign, they're raising awareness. That's one thing. But on the other hand, they put out like an open source repo and they made it sound like, hey, here's a set of algorithms that'll make your stuff fair. And the big danger, right, is that someone would use that and think that like, okay, that'll clear us. And where it gets even crazier, and this maybe ties into a paper that I wrote recently with Alex Choldachova at the Heinz School of Public Policy and Julian Macaulay from UCSD, is that sometimes the algorithm actually could be super horrible from any, I think, like reasonable ethical standpoint, because people have miscast the problem, right? Those simplifying decisions that you made that sort of seemed intuitive, from setting up a toy problem when you weren't thinking about any real world data, might actually result in something that's absolutely horrible, that you would never want to use, right?
What are some examples of that? So
here's a problem. In the United States, our sort of perspective on like discrimination in a lot of contexts is informed by Title VII of the Civil Rights Act of 1964. Now that gives, I think, our dominance in the research community means that maybe like the overall like fairness work is a little bit skewed by technical interpretations of United States law versus other countries which maybe have their own legal precedent. But that's where I think a lot of like thinking comes from. And in that context, there's these, basically the Civil Rights Act has these two legal doctrines that have emerged from it. And one is this notion of disparate treatment, and the other is this notion of disparate impact. And, these are motivated by discrimination in housing and employment in a number of cases. And, disparate treatment is basically about intentional discrimination. So it subsumes discrimination based on like explicit consideration of something that is deemed what they call a protected characteristic, or like membership in a protected class, right? So this could be like what is someone's race, what is someone's gender, and in fact, in the original Civil Rights Act of 1964, there's like some listing of set of protected classes. Probably in 2019, there's some that we would want to include in things that we would think of as kind of like salient, like wedges of discrimination in society that we would want to be especially protective of, that were not included then, like sexual orientation or something. But I guess like 1964 America wasn't there yet, so it's not part of the Civil Rights Act. So disparate treatment is about intentional discrimination, and that includes, but is not limited to, like direct use of that characteristic. So, it's important to keep in mind how the law works versus how math works. With math, we want to say, I want to come up with a crystal clear, simple set of principles that's going to govern any kind of situation that I could possibly encounter, right? It describes the world, or, physics or something like that would kind of operate in this sort of way. The law is more like a patchwork that is plugging in laws in different places to try to deal with different things that are actually happening in the world, right? So there's a set of drugs that are illegal. There's a set of drugs that are not illegal, but, maybe are qualitatively similar. The reason why they're not illegal is because they haven't been abused yet. Once they are, then maybe they would become illegal, right? We would make a law. We say, oh, there's a problem, let's make a law. Right. And it puts us in a weird situation for governing technology, because technology might bring up new problems, but our law is about dealing with certain. When we think of discrimination, when we were creating the law, it's like, who are you thinking of? You're thinking of the racist person who has a sign out says we don't hire whoever. That's one case, right? So disparate treatment, I think, and I want to be clear that I'm not a legal scholar. I'm just a fake legal scholar or something. I'm a machine learning person who tries to be
play one on TV.
tries to be bilingual, maybe more than is standard, but I'm not like, I'm sure that there's a number of people from the other side that know this better. But fortunately, by having dialogue with them, we've had a more refined, we've been able to refine our, analysis on it. All right, so that's one thing, disparate treatment. And the other side is disparate impact. And disparate impact basically is trying to cover those situations whereby you can have what the law calls a facially neutral policy. Facially neutral means like on this, it appears not to in any way like explicitly be taking it, using this kind of information, and yet at the same time it can have an unjustified disparate impact, an unjustified disparity. And so it's really important to think about like what's going on here. And that on one hand, we have disparate treatment. Disparate treatment is a doctrine that is concerned with intent, right? And then on the other side, we have disparate impact, a different legal doctrine, which is concerned with whether or not something is justified. And then we're trying to, people basically look to the law because they say, hey, well, I want to make algorithms that, don't do bad things. So let me look to the law because that's like my existing body of work that I could draw from. But the law talks about intention. The law talks about justification. And, I don't know what justification is in the language of supervised learning, but I'm pretty sure that basically it's not expressible in the like basically we've got an insufficient language. The way that we're talking about machine learning problems is too reductive, and it doesn't possess the vocabulary to express those concepts. Kind of like, I don't know if you've seen Judah Pearl, if you read the Book of Why, it's kind of like that. The way he's ringing that bell, talking about all the long line of statisticians that didn't realize that causality was something that lied outside classical statistics. And like, no matter how hard you try, there's not like just an expression in purely probability terms that, tells you what causality is. You have to introduce like external notation. I think it's a little bit like that. We have the law is coming from this richer family of notions. And we don't know what it means to justify something because all we know how to do is basically say, is something associated with something else? We don't know why it's associated. We don't know how to differentiate, for example, what is the difference between, the difference between if you were to look at like educational outcomes, right, and say what should institutes of higher learning do, in their admissions processes vis-a-vis Black versus white Americans versus white, versus Jewish Americans. And those are two very different cases to think about. And part of why they're different to think about is because, there's this whole background of how that data was created. It's not just is a group overrepresented versus another group, but there's also, what was the process? In one case, I think we have a very deep and well-documented knowledge of systematic, like institutional oppression of one group that, created opportunities and withheld opportunities from the other. And in the other case, you sort of have a group that's maybe overrepresented despite being discriminated against. And these kind of point to different, I think to most people's like ethical sensibilities, different senses about, how you should correct them. But supervised learning doesn't give you those tools, right? Supervised learning doesn't distinguish between these because it doesn't, the tools that we have in supervised learning for trying to address fairness don't look into where the data comes from. So back to those two cases, what people have done is they've tried to formalize, disparate treatment and disparate impact as technical ideas that you can express just as simple statistical parities. And the reason why is because they want to build an algorithm, right? You want to say, hey, here's a problem. I can define it in technical terms. I can fix it in technical terms. So the way people interpret disparate treatment in technical terms is they say, disparate treatment says explicit use of the protected class or intentional use of the, intentional kind of discrimination on that basis, even if, it's not, used directly. Well, let's throw out the intentional part because we don't really know how to model intent. We don't know what that means. It's not even clear if it means anything in the context of a supervised learning model. Whose intent are we talking about? The human, the model? So you throw that part out. And so then disparate treatment just becomes blindness. So it means we just don't use that feature.
Right.
Then disparate impact, on the other hand, we don't know how to deal with the justification part because justification we have to start thinking about where the data comes from. We have to start thinking about what does it, it's too philosophical. So let's throw out the justification part. Let's just look at demographic parity.
Right.
Then, among other things, you say, well, let's say that I wanted to minimize the demographic disparity between two groups while as much as possible maintaining the accuracy of the model, right? How would I do that? And the answer is actually simple. I would go in there and explicitly set the thresholds of the groups differently so that I would accept more people from one group and slightly less from the other than if I had just like run a supervised model and set a universal threshold. And by doing that, you would actually like optimally trade off, the demographic parity versus the accuracy. And then what people end up saying is, well, but we can't do that because we don't want to have disparate treatment. And the question is it disparate treatment if it's in the service of diversity? Mm-hmm. And that actually becomes so the big problem, like where we actually ran into our own problem and got to work through this issue, is that fortunately the set of authors, we had friends who are in the legal community who work on these issues and are really passionate about them and are annoyed when they're talked about the wrong way from the technical community. So they came back to us and said, well, you can't have legal disparate treatment. I'm like, what do you mean? You're like, well, it's by definition, if it's legal, it's not disparate treatment, right? So there was this kind of tension of, so disparate treatment then doesn't actually mean blindness. Disparate treatment means
it's unjustified.
Right. It's like
disparity.
It's not like having disparate treatment isn't just not being blind. It's like having disparate treatment means not being blind in a scenario that's like illegal, unless it's somehow overwritten and considered to be legal. So what we've done, I think that the big danger is we've overloaded these like reductive technical terms with the name of the legal doctrine. So we've purported, at the end of the day, we say we've solved, we've solved disparate treatment, we've solved disparate impact. But what we've solved is like these sort of toy statistical parities. We've characterized these trade-offs. It's useful work, but the big danger, I think, is that we end up sort of misrepresenting to the public like we've solved like a legal conundrum, and we haven't, right? So what we ended up looking at is what then people do, right, is they say, well, you can't have disparate treatment because the law says you can't, even though actually you can potentially, and this is, I think there's all kinds of other arguments, like people are wary of doing anything that looks like affirmative action or calling it affirmative action, whether or not they believe in affirmative action, because there's a worry that, even though affirmative action is legal, that small changes in the composition of the Supreme Court or something could be in a precarious state. So you want to come up with a solution that doesn't rely on, that's a separate issue, I think, from like a strategic angle in terms of pitching policy than from a technical angle. But what we end up doing in this paper is basically look at this problem of like, first, how do these technical notions relate to these legal ones? But then even further, when you try to trade off having this representational parity, this demographic parity, or what we call what they call satisfying disparate impact, or not having disparate impact, but is actually this like demographic parity in a statistical sense with accuracy, and you try to do it without explicitly looking at the group membership, you come up with these algorithms that have very, very strange behavior. And so we start analyzing, what's the behavior of these algorithms? And two really weird things happen. One is that basically, well, you have all these features that are sort of predictive of whatever is the protected attribute, right?
So correlated too.
Yeah, right. Which is sort of why you have a problem in the first place, right? Why disparate impact is a problem in the first place is that, well, it's not enough to just not look at that feature because it's associated with a label, it's associated with the other covariates, like everything's all entangled. If it's perfectly entangled, like in the way that like you could just with 100% accuracy recover that feature, right? Then it turns out, well, because the optimal thing is to just set a class dependent threshold, like, and just move the threshold to sort of in a diversity promoting way, that's what your model is going to do anyway, right? If your model is expressive enough, that's explicitly what it's going to do. So, you've jumped through all these hoops to pretend that you're doing something else, but when the feature is fully recoverable, you're going to end up doing that exactly anyway. So you're only kind of pretending to do something qualitatively different, in which case, why bother? But then the more troubling case is what happens when, everything's correlated, but not perfectly. Like you can only imperfectly infer someone's gender, say, from their non-protected traits. Mm-hmm. And then the weird thing that happens is that if you take a lot of these algorithms off the shelf and you apply them on data, so we looked at CS admissions data and we said, what if we wanted to increase the number of women admitted relative to men? without looking at the gender, right? So that's the thing. That's this kind of problem setup that was adopted by a lot of problems. It says we want to not have disparate impact, but also not have disparate treatment. Keep in mind, I'm like using scare quotes because that's not, they're not really talking about the legal doctrine, but about the. So we tried to not use those terms. So we called it impact disparity and treatment disparity to be like just, and explicitly say in the introduction, like, we use this to just be clear. We're not talking about the legal doctrine. So if you say, I don't want to have either of those, and subject to that, I want to maximize accuracy, what happens? And what ends up happening is the model implicitly is trying to infer what does the gender say. So in our case, gender was a sensitive trait. And then it's trying to use the inferred implicit gender to flip decisions. So basically, you look at what was the threshold that you would have had anyway, and you have some people that are a little bit above the threshold, some people that are a little bit below the threshold, both among, the men and above the women. And what the model's doing is it doesn't know which are the men or the women. It knows which ones it thinks are more likely to be men or more likely to be women. So end up being, if you look at, as compared to the unconstrained model, whose decisions get flipped, and it's, well, one, because there's an inordinate amount of men in the CS admissions data. It's largely just men having their decisions flipped from men who the model thinks are women, having their models flipped to positive, and men who the model thinks are men very confidently having their decisions flipped to negative. And then there's also some flips of women who, and women who the model thinks are men might get hurt by the algorithm. And women who the model thinks are most likely to be women but are a little bit below the threshold are benefited by it. And then you think, well, if you step back, if you think in terms of supervised learning and you just think, hey, what I care about is that there's some group level justice, then, through that lens, you might still say this is worth it. This is okay, right?
Even though it sounds asinine.
Even though it sounds a little bit weird, especially when it's like, well, we could have just gone in there and just set the thresholds a little bit differently. And just, like, our goal was we wanted to increase the representation as a group. Like, why aren't we just doing that? But the weirder thing, though, I think that then this is the part where I think it kind of brings things full circle to like thinking a little bit more like, say, an economist or like a social scientist, is you think not just about a prediction, but a system of incentives, right? Not just I'm making classifications, but I'm making decisions, and this is telling people what they should do to get into grad school, right?
Right.
And it's like, so if you start breaking it down, you look into it and you say, who are the people that the model thinks are most likely to be women? Like, say, among the women, like what are the features that make the model think they're most likely to be women versus men? And it turns out that there's discrepancies based on who your requested advisor is, which area you say you want to work in, things like this, right? And so, like, to me, that's like the scariest part about it. It's not just that it's like a little bit, like, if it was just you're injecting.
Well, it's just all these layers of unintended consequences and potentials for gaming and all kinds of stuff.
And even more than that, right? Because it's not just like unintended consequences. It's like, well, who are the women? Like, how do you benefit from this policy as a woman? You have to be in the field in which women are already well represented, so that it's in the subfield, so that the algorithm knows that you're a woman. But the women who are actually hurt by it are the ones who are like in the field that is underrepresented. Those are the ones who are hurt because the model thinks they're men, right? So, or thinks they're more likely to be men, and therefore thinks it's more likely to get more credit towards its like, equality constraint by rejecting them. And so the danger here, and so like, I don't mean like, I want to be very clear that one, I think we need to do something to address these social issues. And I think it's like a pressing concern of our time. And I'm all for it. I also think we need technical people working on it and thinking about these problems and even investigating the potential of technical solutions. But I think, the danger is we need to be very clear about what is the problem we're solving. And is this a solution anyone should even think about using off the shelf, right? Because like these policymakers are saying we need an interpretability or explainability or some kind of fairness, whatever. And when technologists are showing up because there's a bit of a career cookie to say, hey, I'm working on that and I've made progress. What about my research? The big danger is, well, what if what you're doing actually is really bad? Like, it would be really, really bad for anyone to deploy that compared to even doing something kind of naive, right? And we have to be, I think, just really careful that we don't like sort of create this sense that like we've solved this societal problem in a way where like, oh, you could outsource the judgment to us. We don't need we don't need the kind of think about it in a mushy way. It's like we've actually turned this into a technical problem and solved it. So outsource the like really pertinent like debate that needs to happen to society to the technocrats or something. I think it's absolutely important work in an important area, but the danger that I think we kind of highlight there is there's a huge risk of a certain kind of folly of solutionism.
Well, Zach, it was great getting a chance to finally catch up with you, and definitely lots of important issues here and things to figure out, but not via solutionism.
Yeah. We gotta stay humble.
All right. Well, thanks so much.
Thanks for having me, Sam.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. Make sure you head over to twimlcon.com to learn more about the TWIMLcon AI Platforms Conference. As always, thanks so much for listening, and catch you next time.